Hello and welcome to the presentation of the research I conducted together with my co-authors Markus Bögl and Silvia Miksch. In this presentation I will talk about modeling multi-ensemble datasets using fuzzy set theory. As 15 minutes is not much time, I will gloss over technical details and instead try to convey the general idea and hopefully convince you that this approach can work. So ensemble datasets arise e.g. from simulations, which often model complex real-world phenomena. Therefore, the simulation outputs have characteristics of a scientific dataset, i.e., they are multivariate or distributed over space and time. The output of the model depends parameters and exact model configuration, so multiple runs are needed to account for that. Hence, an ensemble dataset comprises many slightly different copies of a scientific dataset. In this talk we consider multi-ensemble datasets, so you have multiple of the dashed boxes. This can happen if the model outputs multiple scientific datasets to begin with or when you partition an ensemble dataset. This is the data we consider for our talk, a multi-ensemble of maps. In each map we have geographically distributed scalars. And we are interested in the most common member, what features exist in one ensemble but not another, and so on. These are questions that our collaborators, who are experts in statistics and geochemistry, often had. The challenges, of course, are that we have large amounts of data, there are potentially many ensembles, and many members in each ensemble. Precise comparisons between members are not useful due to the slightly different copies aspect. And feature derivation, the process of converting a member to a single number, is too reductive unless you know exactly what you are looking for. The data model you see below describes ensemble dimensions that kind of form a hierarchical containment relation. A parameter setting produces an ensemble, which contains members, which hold features that we find by visual analysis. So we figured that the previous questions look like set relations. The most common member is the one in most ensembles, we could find it by computing many intersections. The question of features in one but not another ensemble can be answered with a difference. But of course there's a problem. Classical sets require perfect matches or mismatches, which are rare in ensemble data, where we usually have similarity instead of equality. This is why we look to fuzzy set theory to build a solution upon. In the following we will rethink the containment relation from earlier as association, just because association is bidirectional and then it's less weird to reverse a question. So the idea is that a member has high or low association to an ensemble if the ensemble contains a similar member, or not. E.g., the member in the callout would be highly associated to ensembles E1 and E3 because they contain it, but not E2 because there's no such member in there. Similarly, we can think of parameter settings having high or low association to an ensemble if a similar setting produced that ensemble, or not. E.g., setting R1 would have more association to ensemble E2 than E3, because E2 was also produced by a big ball but E3 was not. And this principle can be applied to any pair of dimensions. We intuitively used similarity metrics to measure association, so we continue doing that because it seems reasonable. We can capture these associations in a fuzzy relation, which can be written as this table, which we call a relation matrix. Ensembles are rows, members columns in the table. Each cell holds the maximum similarity between any member of the ensemble in the row to the member in the column. Hence, the first three columns, which are members of first ensemble, are perfectly associated. Notable here is that the similarity is in the unit interval, which is a requirement if we want to work with fuzzy sets. We can view the relation matrix as two sets, E1 and E2, on the domain of members and compute fuzzy set queries, like intersection, by column-wise operations. Now I will simultaneously introduce our visualization pipeline and how we configured it to arrive at our example visualization. The model we consider is spatial blind source separation. There's no time to get into specifics, so it suffices here to say that it is a statistical analysis method for multivariate spatial data. Its output are latent dimensions, as shown on the right, which are our maps. As dataset we consider the GEMAS dataset, which is a geochemical survey of 18 elements at more than 2,000 locations across Europe. So this is the data we start with. Each parameter setting, which is a ball-shaped kernel with varying radius, produces one ensemble of latent dimensions. Next we have to compute all pairwise similarities within and across ensemble dimensions. For dimensions involving member data we take the absolute Spearman's rank coefficient. For parameter settings we choose a ratio of the radii. The third step is optional, but we do it here. Nearly identical members can appear in ensemble data, for which we have to account because those would be overweighted in visualizations and data transformations. We propose to remove them using a suitable clustering and use cluster representatives as members. We arrive at the chosen number of partitions by a quantitative process using a clustering quality metric. Then we build relation matrices for all pairs of ensemble dimensions. This process is described in more detail in our paper. Then, almost finally, using the relation matrices, we can compute fuzzy queries. For our example, we consider the intersection of all ensembles regarding their members. This yields all members together with their association degree to the query. The degree is a quantitative variable which we can use in aggregations and visual encodings, or even view it as a source of uncertainty to be carried through our VA pipeline. So in the end we get the degree variable using the red steps which I just outlined. Then we can continue using the pipeline by Wang et al. We continue by an aggregation step, in which we average all members with the weight given by degree. Areas that have consistently low or high values in members then also have low or high average, which we can highlight in the visualization. We expect that these areas correspond to distinct areas in many atlas maps, as SPSS often finds physically relevant components. The map on the left shows the average member in all ensembles, where blue corresponds to low and red to high values. A few noticeable clusters appear. One, orange, is the Gascony region in France, another, green, is the Netherlands and Ruhr area. Especially in the former you can see the triangular shape from atlas maps, land cover, soils and rocks, also in the average. So this seems to have worked out. But we didn't only look at the map ourselves, we also showed it to an expert in geochemistry who is very familiar with the dataset. He identified many expected areas of interest in the average map. We also produced another visualization to show to an statistics expert, specifically the bottom one with the dots. It shows the degree of association of parameter settings to a set of predefined features, which we know should exist, left thumbnail. In the visualization you can see that smaller kernels are less associated, which led to the expert's hypothesis that small kernels may be too small to capture wide area patterns. From that hypothesis we dug into it, producing the big visualization on the right. It shows the number of neighbors per point using a given kernel, which confirms the hypothesis as you want the strip to be significantly away from zero. I close the presentation with limitations and future work. Regarding limitations, we think the biggest is that our approach requires appropriate similarity metrics that use the unit interval. This is to avoid any pre-processing artifacts. Computing fuzzy queries at runtime should be very fast, but there is a potentially significant pre-computation effort necessary. Regarding future work, we think that our approach is promising to be transferred to an interactive setting, which would induce visualizations at the intersection of fuzzy sets, spatio-temporal data, and ensembles. We would have to especially take care that every step is transparent to the analyst to ensure explainability and trustworthiness of the results. And intuitive interactions would be required to build desired queries. Thank you for listening. These are my contact details.